Hello class. We are in section 7.2. This is AP Calculus AB. And we're looking at volume and we're using the disk and the washer method. So if you take BC, you'll learn other methods of doing volume, but we're going to look at disk and washer method right now. So disk refers to like a solid circle cross section of something. That's what a disc looks like. So it's solid all the way through. Washer is a circle, but it's got like a hole in the middle. So I don't know if you've done anything that requires tools, construction kinds of stuff, but that's what a washer looks like. So first we're looking at the disk method. To find the volume, this is example 1, of the solid formed by revolving the region bounded by the graph f of x equals the square root of x and the x-axis about the x-axis. So here is my shape right here. I'm bounding it by my graph, f of x equals square root of x, and the x-axis. So this is my x-axis. So I'm looking at that funny looking, almost looks like a half circle. And I am revolving it around the x-axis. That means I'm taking this shape and I'm making it go all the way around the x-axis. And then what I end up with is this kind of like odd looking football shape. That is my solid of revolution. So on one end of it, I would have some pretty small circular cross sections. In the middle, I'd have some pretty big circular cross sections. But basically what I've got going on is I've got all of these circles lined up end to end, all of those different cross sections. And the way we work in calculus is, remember, we're trying to take, like if I'm finding, let's take a step back. So if I'm finding the area under a curve, what I was doing is I was taking like all of these little like heights or little rectangles, and we're integrating, we're accumulating all of those from like maybe from A to B, right? And I'm adding them all up. And when I add all of those up, what it's doing is it's finding my area. So I'm integrating a height to find an area. So to find a volume, I'm essentially integrating all of those areas of a cross section. So my volume is going to be some kind of thing, some like A to B, and then this is going to be area of a cross section, and then like a dx over here. So that's kind of basically what we're doing today. This is kind of how we're setting it up. There's a lot of different ways to explain this. This is probably like the quick and dirty method, but I'm trying to put this in a way that you as like a brand new first year calculus student will understand, okay? All right, so I'm going to go ahead and erase this, get it out of the way, because I'm going to need a lot of space for this problem. So I want to think about my area of a cross section. Well, my cross section in this case is a circle. And the way I find my area of a circle is I do pi r squared. So I've got to think about what is that radius in this shape. Well, the radius is going to be that distance from my x-axis to the top of this curve. That's going to be my radius. So my radius changes, right? On one end it's really small, in the middle it's really big. But my radius is that square root of sine x. So we are now ready to put all this together. So to find my volume, I'm going to have an integral, and I'm going to go from 0 to pi. So I'm going from end to end, 0 to pi. And my area of a cross section is pi r squared. So pi r squared. But then I know what my radius is. My radius is going to be that square root of sine x. So first I start out with pi r squared, then I replace r with that expression. And now I can go ahead and do a little bit of work. I'm going to put pi in front of my integral because that is a constant. Square root of sine squared is just going to be sine x dx. If you get stuck on sine and cosine and integrating, remember you can always go back and do a little bit of scratch work and say, well, if y is cosine x, what would y prime be? Oh, y prime would be a negative sine x. So I know if I'm working backwards and I'm making this back into cosine, I'm going to have to add in a negative. So I think sometimes the integrating is tricky, but the derivatives, we always remember which ones change sign. So don't be afraid to do that. So I'm going to make this a negative sine And then when we integrate, we now have cosine. So I put my negative in front. And then we're going to evaluate this from 0 to pi. So negative pi of cosine pi minus cosine 0. So let's think about this now. So here is 0, 0 is 1, 0. So my cosine is 1. Pi is all the way over here, right? Which is a negative 1, 0. So, okay, so this means my cosine of pi is a negative 1 minus cosine of 0 is a positive 1. So I end up with negative pi times negative 2, which is just going to be 2 pi. So my volume is going to be 2 pi units cubed, whatever we have here. So the idea is that we're integrating all of those little areas, and that's how we're finding the volume. Let's go and look at a second one. This one's going to be a little bit trickier. They're all a little bit trickier, right? So we start out like this is not bad, and then we're going to look at something that's more difficult. So now we're looking at revolving something not around the x-axis. So now we're revolving it. It says find the volume of a shape formed by revolving this region. So here's my region here, bounded by f of x and g of x equals 1. G of x equals 1 is this line right here. So we're looking at basically this shape right here, and we're revolving it around the line y equals 1. So it makes an even weirder looking football kind of shape this time, but my cross section is still a circle, right? I still have a disc. And the trickier part now is like, what the heck is my radius? So I know I'm going to be integrating, in this case, from negative 1 to 1. We're going to have a pi r squared, and then we're going to have dx. So that's because I'm integrating around my x-axis. I'm going from here to here. But we've got to think about what is that r. So in this case, my radius is going to be the distance between those two curves. So that means my radius is going to be the top one. So it's going to be top minus bottom. So 2 minus x squared, and then minus the 1. So that's going to be 1 minus x squared. So I just took my top curve, 2 minus x squared, and I subtracted this 1 underneath because we're trying to find the distance between them. So to find the distance between something, or the difference, I'm subtracting. So let's go over here and set up our integral now. So from negative 1 to 1, we'll have pi times the quantity 1 minus x squared dx. So we'd want to go ahead and put pi in front. And then we're going to make one more change. Oh, I forgot my square. So the other thing I want to think about here is this shape is very, very symmetrical. If I'm looking at this side of my shape, it's the same thing as this side of my shape over here, right? It's very symmetrical. And it's always easier to work with 0 as a bound. Negative 1 to 1 is a little bit tricky. So instead, what I'm going to do is I'm going to make this a 2 pi. And now I'm going to have my integral go from 0 to 1. Oh, I keep forgetting that square on the 1 minus x squared. I guess because I'm making this square, forget about the second one. I'm catching it, but if I mess up this video, I guess we know what mistake it'll be that I make. So let's go ahead and leave the 2 pi alone for now. I'm going to go ahead and expand this integral. So my 1 squared is 1. I multiply these two together, the 1 and the x squared, and then double it. Plus take my x squared and square, that's x to the 4th. And now I want to go through and actually integrate. So I'm going to have a 1x minus 2x cubed divided by my new exponent 3, x to the 5th divided by 5, and this is all from 0 to 1. So I'm so glad we changed it to 0. It's going to cut the amount of math we have to do in half. So now I have 1 minus 1 to the 3rd power is just 1, so minus 2/3 plus 1/5 minus, when I plug in 0 for all of them, it's just 0. So let's go ahead and get common denominators here. I think I'm going to go over this way because I'm running out of a little bit of space. So 2 pi times, let's go 15ths. So I'll have 15 15ths minus 10 15ths plus 3/15. So 2 pi times 15 minus 10 is 5, plus 3 is 8, so times 8/15. So this would be 16 pi over 15, or 16/15 pi. So our volume would be 16/15 pi units cubed, right? When we look at volume, we're looking at units cubed. So on the back, we're going to look at a whole different thing. So I want to erase a little bit here because I know I'm going to want to probably come back to this picture. And the first two we've done so far have used the disk method. Our shapes have been solid all the way through. So if you think about the line that we're revolving it around, and we look at the shape is touching that line all the way along the line. So when we revolve it around, there's no gaps, there's no holes in the middle. It is a solid shape. But on the next one, you're going to see that that's not the case. So I am revolving this graph about the x-axis. So the graph is bounded by the square root of x and x squared, and I am revolving it around the x-axis. So my shaded region up here, this part of my graph, the part that's bounding together right there and making some cool area shape, is not touching this x-axis. So when I revolve it around, there is a gap inside. And the gap changes shape. It's going to be a pretty tiny gap over by 0, 0. It kind of gets a bigger gap, and then, I don't know, it's like weird. I don't know how to describe that. But the gap is definitely changing size. And then at the end, it's like a really big open circle at this end, right? But like in here, it's kind of a medium circle, and here it's a really tiny circle. So depending on where you look, the size of that circle even is changing shape. But there is a gap there all the way through. So now we're looking at a washer. And when I go to find my area of a cross section, well, my area is going to be the area of the big circle minus the area of the little circle inside. That would give us like this kind of ring around it, right? Because I want it to be all the way around. I want it to have a hole in the middle. So I'm going to do big circle minus little circle. And I'm going to just redraw that because it looks so terrible. So my little circle is going to have a radius r. My big circle is going to have a radius big R. So it's kind of all the way up from the middle for both of those radius. So my big circle would be pi big R squared. My little circle would be pi little r squared. So that's how I would find the area of a cross section. All right, so if I was going to, I could simplify this, right? Or maybe not simplify is the right word. I could factor it. And write the pi in front, and then I have big R squared minus little r squared. So this is going to be now my area of a cross section. So that's what I'm going to be integrating. So to find my volume, I'm going to be integrating that crazy looking pi big R squared minus little r squared all the way from 0 to 1 along my x-axis. But I've got to figure out what are those numbers, or what are those equations? What expressions do I use for those radius? So the one that's my big R is going to be the one on top. That's the one that's further away from my x-axis. So looking at my diagram, my big R is going to be the square root of x. My little r is going to be the one closer to the x-axis, so the one on the bottom, and that's going to be x squared. So what we're going to end up with is the volume, and I'm going to put pi in front, from 0 to 1 of square root of x squared minus x squared squared. And then let's put a dx on the end of this here. So I want to go ahead and square. Square root of x squared is just an x, which is lovely. And then this is going to be x to the fourth. And now I'm all set to integrate. So I'm going to leave the pi in front. When we integrate x, we have x squared over 2. When we integrate x to the fourth, we have x to the fifth over 5. And this is from 0 to 1. So let's go ahead and plug in the 1. We'll have 1/2 minus 1/5. Plug in 0, and it's just minus a 0. Let's go ahead and change everything to tenths. So 5/10 minus 2/10 is going to be 3/10. So we're going to get 3/10 pi, or 3 pi over 10. And that's, again, that's going to be volume. So it's going to be some kind of units cubed. So very different than the last one. So in the last one, just want to kind of go up a little bit. Remember, we had to find our radius by subtracting, and then we had to take that quantity and we had to square it. So that's because I was trying to find my distance between those two as my new radius. And it was a disk. It was solid all the way through. So on this one, because it was hollow, I had to find each of those equations, the root x and the square root of x, and I had to square them first and then subtract them. So the other one I subtracted and then squared, this one I squared and then subtracted. So we want to be really, really careful with the setup. A lot of your tests I'm going to be allowing you to use your calculator on, and that's because we need to be really thoughtful about how we're setting up our integrals to start with. That's what we need to be having our focus on, is not this adding and subtracting and integrating part at the end. So on my last problem, I have this really cool shape. First, you can see from this diagram here and these arrows, right, that we're revolving it around the y-axis. That means everything is going to be in terms of y instead. We're going to have dy. We're going to be integrating along y from like 0 to 2 or something. It says for finding the volume of the solid formed by revolving the region bounded by the graphs of y equals x squared plus 1. So this is that y equals x squared plus 1 right here. Y equals 0. So y equals 0 would be this line right here. X equals 0, that would be the line right here. And x equals 1. So we're revolving that blue shape around our axis. So it's kind of interesting because at the bottom, my graph is touching, right? My blue shaded region that I'm revolving is touching all the way from 0 to 1. This part right here is going to be solid all the way through. It's going to be a disk. And then starting at 1 to 2, I can see what I've got going on is my graph, my blue region over here. This is not touching my y-axis. There's going to be a gap in there. So I'm looking at a washer. So for different parts of the graph, I'm going to be doing different things. And I also have to worry about making sure that everything is in terms of y as well. So I need to have like x equals y, x as a function of y. Now they kind of show you this stuff over here, but we're going to pretend that's not there and just make sure you understand how to do that. So the first clue that I need to make everything in terms of y, actually the most important clue, the right away clue, is that we're revolving this around our y-axis, right? I don't have any other options. We're going to have to make everything in terms of y. So I take that equation, y equals x squared plus 1, and I just solve it for x. So y minus 1 equals x squared, and then I take a square root. So remember, when we take a square root, we're supposed to have plus or minus, but we're looking at something in quadrant 1. I can just basically reject the negative and say that x equals the square root of y minus 1. So I've got that. All right, now I want to go ahead and put all this stuff together. So I've got two parts to my graph. I've got this part of my graph right here, and I've got the part above. I've got this part of my graph right here, right? So first I want to just look at the part that's solid all the way through. I want to look at the disk part of it. So to do the disk part of it, and we'll use some highlighter, I want to be thinking about what my radius is. So my radius is going to be, remember, I'm not going along x, I'm going along y. So this is going to be my radius. And we know that this line over here, this x equals 1, is like 1 unit away from my y-axis. So my radius here is just going to be 1 all the time. So for my disk part of this, I'm going to have my integral from 0 to 1 of just 1 dx. Or sorry, not dx. I said that so confidently, but it's dy. It's really hard to break that habit. We don't need to have the 1 there, except in class. I found that as soon as I got rid of the 1 that was not necessary, we actually had like an absurdly difficult time integrating that, and I'm not really sure why, so I'm going to keep the 1 there. So that's what I'm going to be doing. Oh, and I can't forget circle pi r squared. So this is going to be a pi, this is going to be a 1 squared. I was just really going to write 1 dy, and that's crazy. So I need to put the pi in front. This is 0 to 1. And we integrate. We're basically just going to have a 1y, so just a y, and that's going to be from 0 to 1. So this is going to be, let's see if I can move my paper up a little bit more. I have a little bit more space. So v is going to be pi times 1 minus 0, which is just going to be pi for that first part of it. Okay, so now for the second part, and this is of course going to be the much more complicated part. So this was like my blue integral all the way down. I want to go ahead and do this. And then do this part right here. So that was for the blue part of it, right? So for the second part of it, I am doing, I don't even know what color that is, kind of this coral reddish color. Okay, and so for that, I've got that washer. So I know that's going to be pi big R squared minus little r squared. So my big R is going to be this line right here. That's further away from my y-axis. So it's the one on the right. And that's the one that's just 1. So my big R is going to be 1. And my little r is going to be the curve that's closer to the y-axis, the one that's on the left of the two curves. So that when I say left, I mean like there's my y equals my x equals the square root of y minus 1. Here's my x equals 1. This curve, my line is on the right. This one's on my left of the two of those. So my little r is going to be the square root of, I have no idea why this little message is popping up, square root of y minus 1. Okay, so this volume integral would be from 1 to 2 on my y-axis of my big pi times my big r squared, so 1 squared, minus like my little r squared, which is square root of y minus 1 quantity squared. And I want to highlight this one. So I'm doing my second part. So I think I'm just going to write a plus here. And then I'm going to put pi in front. This is from 1 to 2. And then 1 minus y minus 1. Let's see, 1 minus y minus 1. That's just going to be a 2 minus y, right? 1 minus y minus 1. 1 minus y plus 1. So 2 minus y. And then dy. I bet you thought it was going to be a lot more complicated. So let's go ahead. Actually, shoot, I had space to do more work there. Let's go ahead and do this. Let's write the 1 squared as 1 minus, this is a y minus 1 quantity. I was really worried about fitting in the same number of steps, but it's going to be fine. So then here I want to write pi again, 1 to 2, and then I'm going to write that 2 minus y now. Okay, then my next step is integrating. And this is going to be, let's see, when we integrate 2, we have 2y minus y squared over 2. And this one's from 1 to 2, so this is going to be a little bit trickier. So let's see, when we plug in 2, 2 times 2 is 4, minus 2 squared is 4, divided by 2 is 2, minus, okay, now we're going to plug in 1. I'm trying to really go slowly. 2 times 1 is 2, minus sign for the problem. When we put 1 into the second part of this, 1 squared divided by 2 would be a 1/2. So this is what I have right now. So pi plus, and remember this is all from that second part of it, right? This is all from the second part of it. So I'm just kind of color coding it. So this is going to be pi times 4 minus 2 minus 2. Like these guys are all going to be gone. but I'll have a minus minus, I'll have a positive 1/2. Okay, so from the bottom part I have pi, from the top part I have a 1/2 pi, so my overall volume is going to be pi plus 1/2 pi, or 3 pi over 2. Of course, units cubed. It's interesting that the volume for the top part ends up being exactly half the volume of the bottom part. Very interesting. But this last one was, of course, the most difficult because we're combining these different shapes. So just kind of to go through what we've got, we're looking at now revolving shapes around the x or the y-axis. Some of our shapes that we're revolving are going to butt right up against the line we're revolving them around. So they'll be solid all the way through, and they'll make a disc shape. Some of the things that we are revolving are not going to be touching our axis that we're revolving around. And it could be an axis, it could be a line, right? It doesn't have to be the x-axis or the y-axis. We saw that with the second example. And if they don't touch up against it, it creates some kind of a gap or a hollow in the middle of our shape. And so we end up with a washer. And so we have to treat those differently depending on if we have a disc or a washer. So we want to make sure that we understand the graphs first. We want to make sure we know if we're using a disc or washer method or a combination of both. We have to think about, are we revolving around the x or y axis? And then every single time, once we figure out all of those things, right, we're going to set up our bounds. We're going to have our area of a cross section. Which for today are some kind of a circular thing, right? And then we're going to have either a dx or a dy. As always, if you've got questions, please make sure that you ask and get help.